Good afternoon, everybody, or good morning, depending on where you are. This is Tim Lankish here from CAE Services. We're going to give it a couple minutes here while people make their way into the broadcast here. So stand by and we'll get started shortly. Okay, I think we're going to go ahead and get started here. So welcome, everybody. Appreciate you taking time out of your day to join us here for our webinar. My name is Tim Lankish. I'm the Director of Engineering here at CAE Services. We are a Moleflow consulting firm and an Autodesk reseller as well for the Moleflow products. We've been doing this Ask the Moleflow Experts series for quite some time now, and we decided a little while ago to do a Back to Basics series within this webinar series. So the topic for today is cooling analysis. And so everything related to cooling analysis is what we're going to cover. Just a little bit about CAE Services for those of you who don't know much about us. We're located in the Chicago suburbs. We were established back in 1988. We have the most expert certified Moleflow engineers in the world. As I mentioned, we're an Autodesk partner. We've completed on our consulting business some 30,000 plus projects. And there's our website if you'd like to learn a little bit more. This is a little bit about me. My background is in physics and math. I've been here 29 plus years now at CAE Services, expert certified, and I do all the training here for the Moleflow products. And within our own consulting business, I've trained more than 15 expert certified engineers. I've contributed to trade magazines and been a presenter at the Moleflow Summit. And by the way, the Moleflow Summit is coming up, so those of you who are interested, just Google it. It is online again this year, unfortunately, but hopefully next year we'll get back to being in person. So just a recap of this webinar series, and you can find if you wanted to watch any of these other webinars, we replay some webinars from time to time, and I believe we can send a link to some of these if I'm not mistaken. But like I said, it's the Back to Basics series. It's focusing on the building blocks of Moleflow analysis. And in our first webinar, we did a little bit of an overview, went through some Moleflow history. We talked about just, kind of from a 30,000 foot level, what Moleflow's capabilities are, what the benefits are. And the main point there being that mold flow analysis leads to problem solving. It gives you good, solid, accurate information for you to help formulate a solution to a given molding problem. And in most cases, the best way to use it would be to avoid those problems in the first place. And then we went on to the second webinar for filling analysis, where we talked about the best use of filling analysis being determining gate locations, avoiding aesthetic problems like blush and things like that, knit lines. We talked about the ability to develop a large processing window so that we can put the molder in a position for success, because there's so many things that happen at the press that the processing team or mold flow can't necessarily account for directly in its simulation. So we want to develop the largest processing window possible so that we have a better chance for success. And then, setting all these things up in filling analysis kind of snowballs. It sets us up for success down the road for packing, optimal packing, and reduced warpage. And then in the third webinar, we went on to packing analysis. And the two main things in packing analysis that we hit on were what we do to get the shrinkage level right and what we do to achieve uniform shrinkage. So those are the two main things that we focus on for that, because the mold maker is going to pick a shrinkage level based on several things. The material supplier is going to have some input. The molders are going to have some input based on their experience with certain types of part designs and so forth. But the mold maker also makes an assumption, typically, that the shrinkage is going to be uniform. And anyone that has any experience in the injection molding industry would know that plastics don't shrink uniformly. They just don't. Wall thickness, distance from gate, temperatures, a lot of different things play into how the material shrinks. And the mold maker has to make an assumption about shrinkage being uniform. Some cases can do it, different numbers in different directions, but by and large, it's a uniform shrinkage number that they're targeting, and we as analysts have to try to make that assumption as true as possible. So that was packing analysis, and now we're on to the next step, cooling analysis. So we're going to get back to the cooling basics. Doesn't matter what we do in cooling, whether we're doing conformal or how we're doing cooling, the fundamentals don't change. We'll talk about that a little bit, but how do we take advantage of them? There are different types of mold flow cooling analysis, and we'll talk a little bit about them. Cooling design shouldn't be an afterthought, right? And they often are, because there's so much going on in a given mold design sometimes that let's just put cooling wherever we can get it, right? That's often a mindset that unfortunately is out there, but cooling design really shouldn't be an afterthought. So the key message we want to get across today is that we can achieve cooling uniformity and efficient cooling proactively using the analysis. So seconds matter. Most people don't know if their molds are optimized or not, I would say, and oftentimes they just settle for good enough. Like I said, it's often an afterthought, and there's always room for improvement. And it's the cooling analysis that's going to help us take some of that guesswork out. So I mentioned previously that the fundamentals don't change no matter how we're doing cooling. It's a process of conduction and convection in the mold. Excuse me, the conduction is heat transfer in a stationary solid or fluid medium that have surfaces at different temperatures. And if you like equations, that's a general heat flux equation that governs conduction. And for convection, rather than heat transfer between solids or fluid medium, now it's heat transfer between a surface and a moving fluid that are at different temperatures. So there's the heat equation there. And we're going to focus on the two main aspects of cooling analysis, one being uniformity, the other being efficiency. So let's start with the uniformity. part of it. The pitch of our cooling channels is what's going to control the surface temperature uniformity. Here's a couple of different designs. We just have a basic flat plate to help us illustrate this. Imagine, and we see this oftentimes in many tool designs where the cooling design is very basic. You have a couple of channels traversing the part here, and you can see a fairly wide range of temperatures, anywhere from the 140s up to the hottest area there in the center, around 170 degrees. And then we add another channel to take care of that little hot spot there, but we still have some variation, right? 146 up to 162, 16 degrees, or in this case, I guess it's actually 18.3. And then we add more channels and we see that temperature variation reduced. So you can see just by relatively small changes to the cooling design, we're able to achieve more uniform temperatures, and that's what we're after. So that's pitch, that's distance between cooling channels and the number of channels. Now we're going to talk about depth. The depth is the distance from the cooling channel to the part surface itself. So here we have those 6 channels with poor depth, too far away from the part. You can see it's only 5 degrees variation, but when you compare it versus putting the proper depth in there, you get nearly perfectly uniform temperature distribution there. And it doesn't take much of a temperature differential between the two sides, the core and cavity side, to create some warpage. Now, granted, this is a flimsy flat plate, but again, here for illustration purposes, that 5 degree temperature differential produced over a 0.5 millimeter of warp. So you get into situations where the temperature differential gets to be 20, 30, 40 degrees in some deep cores, and now you're talking many millimeters of warpage in some cases. So that temperature differential between two sides of a part leads to thermal bending, and that thermal bending can be excessive. And there are ways to improve the cooling uniformity to avoid that. So the first solution is going to be add or move water lines around. A second solution would be to add higher conductivity inserts. And a third solution would be conformal cooling. So we'll talk about each one of those. So improved cooling line placements. So this is an example I've shown many times, but it's a great illustration of the issue here. So we have this deep pocket in here, a very tight corner, kind of a V-shaped corner that's trapping heat. And the original cooling design has a cooling line going through the slide here, steel slide. And you can see the temperature variation here is in the, in the hottest spots, it's getting up to 240 degrees. In the other areas here, it's showing in the low 100s. So quite a temperature variation over a short distance. So the first step was to try to add some cooling lines, and you can see by adding some baffles, and we even stepped them a little bit to try to get farther into the tight corner there. We're still getting some pretty high temperatures in there, 223 degrees. In this area over here, we dropped at almost 32 degrees. So good improvement, but still pretty high temperature buildup there. And when you compare the warpage between the two, this is a glove box door, and that latch area right there, with 1.5 millimeters of warp in that Z direction was going to be excessive. But we dropped it down to a millimeter, and we wanted to see if we could get that even better. So we looked at adding them, instead of making the slide out of steel, making it out of Mold-Max and see what that would do. We kept the baffle design, still a good idea to do that. You never want to have higher conductivity inserts without cooling lines in them, or else you just get a piece of metal that heats up even quicker. So always make sure that you have cooling lines inside your Mold-Max or AMCO or whatever it is you're using as a higher conductivity piece of metal. So we introduced this Mold-Max slide. Like I said, kept the baffles. And here's the temperature reduction from the no Moldmax design compared to the Moldmax design. You can see now we dropped it 70 degrees from where it was, kept the baffles there as I mentioned, but dropped it 70 more degrees. So now we have pretty darn uniform temperature distribution in that tight corner. And if we compare to the original warpage of a 1.5 millimeters, now we're actually going in the opposite direction. So we almost did too good of a job there, and we're warping about 1/4 millimeter in the opposite direction. But that was okay. We're okay with that. So that's an example of using higher conductivity inserts along with moving some water lines. Now we're going to talk a little bit about conformal cooling, and conformal cooling is kind of all the rage these days, right? Lots of different ways to do it. This is just one example. This uses a company called HTC. Actually, I have a slide that shows how that's done, but essentially there's a brazing process that goes on, sticking different pieces of metal together rather than building it up by like a 3D type of a 3D printing type insert. Doesn't matter which way you do it. The idea is to try to get cooling lines that are closer to the surface of your part in areas where it's more difficult to get conventional drilled channels. Here's an example of a propeller fan blade type application. You can see we've got a single cavity mold. We've got a tight core side geometry where it's difficult to get drilled channels up into the deeper recesses of that area. And we have some thick walls in the hub as well. So a bit of a challenge for cooling that area. You can see with the conventional cooling design, we have the baffles sticking up into there, harder to get close to the surfaces. I suppose you could probably angle these baffles a little bit and get a little bit closer, but you know, we're starting to get into thin steel conditions there. And on the both core and cavity side, it can be more difficult to follow the fan blade contours with straight drilled channels. So this is what the conformal cooling design looks like. The cooling lines conform to the part surface geometry. We're able to reach the deeper cores. We added cooling to the cold sprue as well. And as I mentioned, it's HTS Corporation that does this type of conformal cooling. So look them up if you're looking for another source for conformal cooling. If we compare results, we look at the conventional cooling, and you know, after 90 seconds into the cycle, we're looking at the temperatures. We have some very hot areas here and these deeper recesses that are thicker. And if we try to match this temperature profile, a couple things happen. Notice the difference in the time. You know, we knocked 28 seconds off that cooling time. And we also achieved more uniform cooling. You see the upper recesses of the core here, the surface temperatures are much cooler, went from green down to blue here. So almost 50 degrees of improvement there. And, you know, to get the thickest area here down to the same temperature took 28 seconds less. So major improvement all around by using the conformal cooling, both on the uniformity side and on the efficiency side. So let's talk a little bit more about efficiency. Cooling efficiency focuses on the cooling lines themselves. We're going to try to make them turbulent. We're going to size the channels properly to achieve that, and we're going to circuit them properly as well. So we got to ask those questions. So achieving turbulent flow in your cooling lines and the coolant itself allows us to reduce the cooling time. Here's a comparison between laminar and turbulent flow. So the two pictures on the top represent laminar flow at a 67-second cycle. That laminar flow gets our Reynolds, it has our Reynolds numbers in this case in the 1,000 to 1,300 range. So anything below 2,400 for your Reynolds numbers are considered laminar, and our heat transfer goes down considerably when we're in that condition. And notice also we have a higher temperature variation here. We go from 165 up to 198 on that surface. When we're able to achieve turbulent flow, our cycle time goes down by 7 seconds to 60 seconds. Notice our turbulent range is in the 10,000 to 13,000 range in this case. Technically, turbulent flow is 4,200 Reynolds number and above. We tend to try to stay far above that just to make sure we're not getting anywhere close. We certainly will accept lines that are getting closer to that 4,200 range, but if we have enough pump capacity, we want to try to drive that up a little bit out of that area so we don't even, approach that boundary. But notice also what happens here is it reduced the temperature variation as well. So remember, cooling uniformity is something we're also trying to achieve. So turbulent flow helps us do that as well. Then we get into these cases where the cooling lines themselves start to matter, especially on these smaller parts with tighter cores, and we have a bunch of bubblers trying to cool those areas. How we design those channels and what sizes we use for the bubblers can matter. So this is a 64 cavity mold, and the bubblers are restrictive. The parts themselves are just over 3/4 of an inch in diameter. And as you can imagine, with the high cavitation, they want to get as fast of a cycle as they possibly can. And by improving just the cooling channel design, there's potential for savings of about $183,000 per year. So it's pretty impressive when you think about it. But how does this look in analysis? So when we analyze the original design, we noticed that we were not able to achieve turbulent flow. The cooling line was too restrictive. The flow inside the bubbler tube itself was relatively okay, not restrictive, but the downside was when it fountain flowed over top of that bubbler and went to its return, very restrictive between the bubbler the outer tube diameter and the drill size. So Reynolds number was very low. If we made one quick change to the design, we upsized the diameter a little bit, but now it put us in this transition between 2,300 and 4,200. Better, but still inefficient convection. We can do better than that, and the final design looks more like this. Increased diameters, increased bubbler tube size, etc., and we match the flow between the inlet and the outlet much better. We get a Reynolds number above the turbulent plateau there, and we're able to achieve less restrictive flow. That less restrictive flow leads to, as you can imagine, some cycle time improvements. And if we go through the stages, the same 3 stages, we started off at 7 seconds to get to an ejectable temperature, and we reduced it by 2.1 seconds, which doesn't sound like a whole lot, but when you're molding a 64 cavity mold 24/7, 365 days a year, again, that $183,000 of profit can be realized by reducing that cycle time. So now we'll talk about proper circuiting. So that was changing cooling size, line sizes to improve our turbulence. Now what do we do when we've got a very large mold and we have a lot of water lines that we have to figure out what to do with? This is an IP carrier, and we want to try to maintain temperature uniformity, but use fewer GPM to do it. And in this case, the potential savings was around $206,000 per year. So with proper circuiting, we should be looking to achieve only a moderate temperature rise. Okay, so Here's what happens when we have no circuiting. We have every cooling line has its own inlet and outlet. Okay, so great, we got very, very uniform temperature rise, right? Less than a degree change in the coolant from inlet to outlet, very uniform. On the other side of the spectrum, what happens when we start looping all these lines together, right? Excessive circuiting. Now we have, all of these lines on the left connected together, all the lines on the right connected together in another circuit. So 2 circuits for the whole cavity side here. Now we're looking at about a 14-degree temperature rise in the coolant. We'd like to keep things below 5 if we can, preferably 3. So that's no good, and that leads to temperature variation. But when we do things just right, this sounds like Goldilocks and the 3 bears, right? Too little, too much, and just right. Proper circuiting leads to a temperature rise that's less than 3 degrees in each of the channels. So when we look at the number of GPM each requires, and this is where we get into trouble, right? If you want perfectly uniform cooling, less than a 1 degree temperature rise, it's going to cost you 134 GPMs. You may or may not have that many GPMs available to you. Most people don't. Again, going to the other side of the spectrum, excessive circuiting is great. It doesn't require a whole lot of GPM. Pretty much anybody can put 5.7 GPM in a mold, but that leads to the temperature issue. So if we do it right, proper circuiting only requires about 45 GPM. So this is the happy medium. So there is a way to achieve uniform cooling without costing you too much water. And then if we look at the temperature uniformity part of it in the part itself, not just in the coolant. So when we have no circuiting, again, that's going to cost us 134 GPM, but very uniform temperatures. We only see about a 14-degree temperature variation, 14, 15 degrees, which is acceptable. When we do proper circuiting at the same cycle time, notice we've got about the same temperature profile. So we didn't lose anything there. When we did improper circuiting, notice how this area over here and this area over here start to increase in temperature. So just by the fact that you loop too many lines together, that increase in the temperature of the coolant also has a corresponding increase in temperature in the part. Okay. So what that would cost you is cycle time. So to get back down to the temperatures that we had when we had circuiting done right, it was going to cost you an extra 20 seconds. So there is an impact when you do things wrong when it comes to circuiting. So talked about the fact that there are different ways to do cooling analysis in Moldflow. Here's just a quick list. We have what we call CFD, or Computational Fluid Dynamics coolant flow. We have 2-shot cooling. We have transient cooling. We have induction heating, and we have rapid heating and cooling. I'll touch on a couple of these. The CFD coolant flow is kind of cool. This is for those cases where you don't have, a standard shape of a cooling line. There's different modeling techniques for different types of cooling channels in the standard Moldflow cooling analysis. But when we get into these, I'll call them oddball cooling designs, you have to go to what's called a CFD analysis to model these shapes up that don't conform to a standard cooling line, like a circular or rectangular type cross section. So you can see here how the flow comes in through these channels here, and then it's distributes itself. We're tracking the velocity of the coolant flow, and you can see most of the flow goes straight down and hits the bottom, and then starts to recirculate here in this area. So we can use this to help test a bunch of different designs and see which ones are best in distributing the flow, the coolant flow, a little bit more evenly. Transient cooling analysis allows us to track the temperature at any one location in the mold throughout the full cycle. When you do a standard mold flow cooling analysis, we're generally tracking the average temperature through the cycle. And what we found over the years is that these transient cooling analyses are great for direct correlation, but we're still getting the same results in terms of how does it impact our cooling design? Do we have to do a much longer analysis to be able to recommend the same type of a cooling design? And generally speaking, the answer is no. So this is for much more nitty-gritty analysis, more granular analysis in terms of getting the nitty-gritty detail results at every point in time and every location within your mold, which is really nice for some things, but by and large, the cycle average numbers are adequate for getting the right cooling design. We can also track the number of cycles it takes to get to a steady state situation when we do what we call a transient from production startup. So we can look at multiple cycles and track the temperature over time as it relates to that. Two-shot cooling, this is where first shot cooling affects the second shot because the first shot may insulate the second shot from the coolant. So still have the same objectives as a standard cooling analysis. So this is what a model looks like, and of course the mold's going to rotate from position 1 to position 2, and we have heat transferring back and forth between those two stations during the cycle. We have to define what we call rotational elements in a mold flow analysis, and you can see you'll track in the black there, it's tracking station 1 temperature over the 2 cycles, and then in red station 2 there. Here's kind of what it looks like in an animation through a full cycle. That's kind of cool. And you can see the temperature rise in station 1 and then rises over here, station 2. So interesting analysis. So, but the question is, really what's best for you? So all cooling analyses present some opportunity, right? Opportunity for better parts, for increased profitability. I would add fewer headaches to that, right? Less troubleshooting in your mold. Warpage analysis, and we'll talk about it in the next seminar or webinar, but one of the first things I see molders look to when it comes to warpage is the cooling, and rightly so in many cases, but you don't know until you get into it, right? And that's what mold flow analysis helps you flesh out. How much of your warpage is due to the cooling? But there are other things too, cycle time being the biggest one of them. How do we improve our cycle times? And there's an awful lot of trial and error that goes on at the mold, at the press to figure that out. So that's where the cooling analysis comes in. It's an opportunity to see what your limits are based on your design, because you don't know what those are until you get to the mold if you're not doing this analysis. But no matter what type of cooling analysis you're doing, we're going to be looking for temperature uniformity. We're going to be looking for coolant flow efficiency. And we can play the what if scenario to find out what's best. So again, mold flow analysis is great, but it's got to lead to problem solving. So how do we solve the problems of cooling uniformity and cooling efficiency? For cooling uniformity, we talked about adding or moving water. Remember, we added those baffles. We looked at higher conductivity materials like beryllium, copper, aluminum, what have you. And then in the cases where we want to push the envelope, we can go to a more intense solution like a conformal cooling application. And again, there's a lot of different ways to design and manufacture conformal cooling inserts. On the efficiency side, always need to get to turbulent flow, and we're going to do that by sizing our channels properly. And then when we have them sized properly, we're going to circuit them properly so that we're achieving turbulent flow, we're achieving uniform temperature, and we're doing it with a minimum amount of water. So some general ideas, as I preach in every webinar, plan ahead and have mold flow analysis done proactively. It doesn't matter if it's filling, packing, cooling, warpage analysis. You know, of course, cooling is what we're talking about today, but it's important for anything in injection molding. Have mold flow analysis done way ahead of time so that you have the chance to be able to solve or avoid problems before they become problems at the press. And you know, it's best to do them in the earliest stages of product development. Some more specific ideas, you know, for molders and OEMs, insist on the mold flow analysis. Do it yourself or use an outside source. I know a good one if you're looking for one. Know your GPM for each cooling line. You know, that'll help you determine whether or not you've got turbulent flow. And do the math. What does so many seconds of cycle time savings mean to you? I'm sure most molders are keenly aware of that number, but you know, make sure you're checking that out. For part designers, try to avoid difficult to cool areas wherever possible. When you are tempted to use extremely thick sections for load bearing applications, for example, or whatever it may be, try to core those areas out and use ribbing for more structure if you can. We want to try to have as uniform of a wall stock as we can possibly get in any plastics design. Use analysis to help identify those areas. You know, Mold Flow Advisor can even come into play here, just to get again a 30,000 foot view of what you're looking at. But obviously, a full-blown mold flow cooling analysis and Mold Flow Insight is going to give you more definitive solutions or answers rather. And for you mold makers out there, be creative in your mold designs and test them using analysis. And then, you know, if there are areas where a design isn't adequate, use some of the suggestions from analysis to help improve on the cooling. So what's new at CAE Services? We're going to be exhibiting at the PT Expo in Chicago. It's at the Rosemont, or in Rosemont, right outside of Chicago, right by the airport. That's March 28th to 30th. I believe we're in booth 132, so stop by, say hi if you're going to be there. Love to see you. We are going to be doing stress analysis, FEA for molds, you know, mold cracking, things like that. So look for that in the upcoming months. That's an important thing to mold makers and to molders, of course. You know, after so many cycles, molds can break down and some cases have catastrophic failure. So we want to try to avoid those types of things before they become a problem at the press. We have a new gentleman in town, so to speak. He'll be working out of Michigan. His name's Justin Bertovic. A lot of you may know him from his days working for a prominent hot runner manufacturer out there. So Justin's going to be on our account management team here. So see Justin around the Michigan, Windsor area, say hi to him. Talked about our Autodesk partnership. We have software sales, training in mold flow. Look online or give us a call if you are a mold flow user and you need training in any of those software products, and mentoring as well. You know, it's one thing to be trained in mold flow, but I think the real learning comes when you have someone that knows the software inside out and knows how to use it to solve problems. So we are here for mentoring as well. Building expert analysts. So I mentioned the training part of it. Our next Mold Flow Fundamentals class is at the end of February, but again, look online for the calendar or just give us a call if you're looking for something more specific. We'll be doing these webinars monthly. Some are going to be repeat, others going to be new material. Our next Back to Basics webinar is going to be about warpage analysis, so that's always a big topic. Moldflow office hours, if you want to pick a topic and spend hours talking to me about it and picking my brain or anyone's brain here about anything Moldflow related, you can sign up for Moldflow office hours. I mentioned our website earlier, so go there if you want more information, or you can follow us on LinkedIn. With that, I am going to open up the microphones for questions, but you have to raise your hand first. So use the webinar control box. If you have a question, go ahead and hit the raise hand button and we'll try to answer your question. I'll open your mic up and then you can answer or ask the question directly. I do have one question in the questions box, and that question is, can the cooling analysis help to address part windage? So windage is a warpage topic, but yes, absolutely, cooling analysis can help address part windage. So windage is the process of biasing the tool in the opposite direction of the expected warpage. And anytime we do windage analysis here at CAE, one of the first things we want to do is remove as much warpage as we possibly can using conventional methods first. So windage would always be a last option. So if we do our warpage analysis and we determine that cooling is the main culprit, then we want to address the underlying issues there. Is it a part design issue? Is it a cooling design issue? Can we fix things with better processing, getting turbulent flow, better circuiting? Can we fix it with higher conductivity inserts? Could we go to conformal cooling? So all of those things that I just talked about would be on the table to help reduce warpage. And then if we've taken as much warpage out as we possibly can in cooling and through packing and filling issues, part design issues, if we're at our last straw, then windage is certainly on the table. So yes, short answer is it can help, but I don't want to have to rely on like a cooling process, if you will, like having different temperatures on different sides of the mold, like running 40-degree differential in the water temperatures between core and cavity. I'd like to try to avoid that. There's probably a better way to solve that problem than just changing the water temperatures, because then you're just molding in stress, and then you might get into a situation in a high temperature environment where that stress is just going to relieve itself in the form of warpage later down the road. So we want to try to hardwire our solutions into the part design or the mold design where we can, and not have to rely on processing if we can avoid it. Okay, Sean has a question. Sean, I'm going to open your mic. Sean, you still there?
Oh, okay. Yeah, can you hear me now?
Yep, I got you.
Yeah, I typed the question. I don't know if it came through, but yeah, I was just curious as to which mesh you usually recommend to just that you've seen in your experience provides the best warpage results, or does it kind of depend on the application and the type of material we're using?
Yeah, you certainly answered your own question there. So the type of the part design plays into it. Thick, chunky parts tend to be more 3D. The thinner type parts, most parts, generally speaking, are considered thin walled parts in injection molding. There are two types of mesh. There's the mid-plane and the dual domain. You got to be careful with dual domain meshes. They absolutely can get you decent results, but they are going to miss some things like buckling. Can't do buckling analysis, and I've solved many problems that are buckling. So when you get those situations where Moldflow in a dual domain mesh is predicting the opposite direction of warpage, for example, sometimes it's because it missed buckling. The other part of the equation is material testing, and we'll talk about this in the next webinar, but having good solid shrinkage data in the form of CRIMS data, what we call CRIMS data, is used only for midplane and dual domain meshes, and I'll call that the creme de la creme of shrinkage data. 3D warpage analysis does not rely on that. 3D analysis, generally speaking, tends to underpredict warp compared to midplane and dual domain models that have CRIMS data. So it's a big, long discussion, but generally speaking, you have to choose the right type of mesh for the right type of situation is what it generally boils down to.
Got it. Thank you.
You're welcome. Okay, Tarun has a question. What is a reasonable mesh size across the board to get decent results? You know, if that's a discussion we get into in MoldFlow training. It depends on the part is the bottom line, and the part design. You certainly have to pay attention to mesh size when you have changes in geometry and so forth. But that's a fairly long discussion. Just suffice it to say that mesh size is important to get good results. Victor has a question. Victor?
Yes, can you hear me?
Yeah, I can hear you.
Okay. Regarding the boundary conditions, I mean, the inlet in the cooling, what is the temperature recommended for the inlet water temp, for example?
That's material dependent for the most part. You want to rely on the material supplier's recommendations for the best surface temperature of the material at ejection, right? You know, it's tempting just to say, well, let's make it as cold as possible so we can get the best cycle time. That's not always the case. You know, sometimes very glossy appearance is needed. So you might want to rely on a much higher temperature than what the material supplier recommends. You know, when you're ejecting a part, you essentially are trying to build modulus. You're trying to build stiffness in the material to the point where you can eject the part, right? So what are the conditions for getting stiffer material? You know, you have to build crystallinity. Crystallinity leads to stiffer material, and the conditions. You know, if you follow a guy named Mike Seppi talks about having higher mold temperatures to build crystallinity and lower melt temperatures. So a lot of that depends on just kind of where you're going, what kind of surface finish you need. It's not always the case that you just reduce the coolant temperature to get better results, quicker cycles and so forth. The best way to achieve quicker cycles is through good, solid cooling design and through achieving turbulent flow. Does that answer your question?
Yes. So it means that it's related with the mold temperature recommended by the material
That's
supplier.
correct. Yeah,
Okay.
and generally speaking, the temperature that you use for the inlet temperature is going to be some, 10 to 20 degrees C below what the recommended surface temperature is. It really just depends on your coolant design. So if you have cooling lines that are closer to the part surface, then you can probably make the inlet temperature a little bit closer to the surface temperature you want, and vice versa when the cooling lines are farther away. So yeah, it just depends on the material, depends on your cooling design, and that's why you use analysis to see if you're able to get the surface temperatures you want at ejection for the given material within the cycle time that you're trying to achieve.
Okay, so in general, 5 or 10 degrees below.
As a starting point, yeah, and then just then you let the results speak to you.
Okay, thank you.
Yep, and that's 5 to 10 degrees C, by the way. So, okay, any other questions out there? David, looks like you have a question.
Yeah, can you hear me, Tim?
Yeah, I can hear you.
Okay, thanks for taking the question, Tim. A couple comments that you made throughout the seminar just drove a question in my mind, and I thought maybe you could help me out. First of all, this is just sort of like something buried in the software. But when you're doing a cooling analysis and we have straight through lines, and maybe you have a GPM or a flow rate specified for that line. If that's the convective side of the heat transfer, right? You got conduction and convective through the heating. You have to come up with a heat transfer coefficient, right? How does Moldflow determine that? Do they use one of the standard empirical relationships between Reynolds number, fluid temperature to get that, or?
Yeah, so the heat transfer in, as it relates to coolant flow. And let me get a pen out and I'll draw this. Can you see that okay? Let me get a different color going here.
I got it.
Yeah, so if you were to chart the heat transfer coefficient as a function of the Reynolds number, it would look something like this. Okay, so from here to here is that transition zone, and that's the 2400 up to 4200 here. Okay, so you see what happens here, and this is all hardwired as the equations in Moldflow. Okay, so that heat transfer coefficient from laminar flow up to turbulent flow changes in Moldflow, and you can see it. I mean, you saw some of the results that I showed, and this is about a 7 times difference in that heat transfer between turbulent and laminar. But what happens when you get past this turbulent plateau is it just rises, very slowly. So you're wasting a lot of water out here by going, we'll call it super turbulent, right? So you don't want to put it right past 4,200. That's kind of why we go out to 10,000, just to kind of be safe. But anything beyond that, we're wasting a lot of water. If we get into a situation where our GPM start to get compromised at this 10,000 range, we can dial that back a little bit. But generally speaking, that's kind of where we want to be.
Okay, no, Tim, I understand that. It's the curve itself.
Yeah.
Do you use some type of an empirical relationship? There's a couple standard ones in the literature. I was just curious, which ones do you guys use to generate that curve?
I don't have access to that information, honestly, because I don't write the software, and I don't think that Moldflow would actually give that out. But I do know for a fact that yes, it is an empirical relationship between the two.
Okay.
And as you said, I suspect there's more than one out there, but I think there are probably generally accepted numbers. I've never specifically asked for that. I don't know that Autodesk would be willing to part with that number for proprietary reasons.
Fair enough. The other thing too, as you mentioned, when you're using a high performance alloy for better thermal conductivity, you mentioned that really it doesn't make much sense to use those unless you can put water directly on a high performance alloy.
Correct.
It's funny. We also build molds here, and we have some old mold designers and tool engineers and guys out on the shop floor that state the same thing. However, we do a lot of analysis, okay? We do quite a bit of thermal analysis here, and a lot of times we'll design our thermal system based on our homegrown methodology, and we can validate that design once we have it with a Moldflow analysis, okay? But we've done a lot of work that would be contrary to that statement, okay? And it kind of makes sense to me, only because I've actually seen it work. But when you introduce a high performance alloy, like say Momex or Amcloy 940, or even pure copper as an insert material, what you're doing essentially is you're lowering the conductive resistance between these 2 points, okay? If you didn't have, if you kind of just put it intermediately between where your water was and the steel you had, and you added the high performance alloy, you're kind of reducing the thermal, the conductive resistance between your heat load and where in your cooling fluid. So you can drive a higher heat, or you can drive the same heat flux through that with a lesser temperature difference. I was just curious where you picked up that thought process, okay? Because I encounter it a lot, but I can do analysis that says no, it is beneficial. Now, yes, it'd be much better if you had water directly on it. Understand that, but you can reduce like the bulk conductivity of that mold component by using those alloys. Am I off base, or is my question wrong? You got to tell me.
No. I think a lot of it depends on the specific design. I see it both ways. There are cases, as you mentioned, where you can absolutely get some benefit to there. A lot of it depends on that air gap between the the insert and the steel that surrounds it as well. So obviously you have to have a very good fit, a good thermal. You don't want the air to be the thermal barrier. So I guess the bigger point is a metal insert, whether that's steel or a high performance alloy, with and without water is night and day. I think that's the bigger point here. But there are certainly cases, and I've gotten feedback from a lot of customers where it has been the case where they have the high performance alloy and it absolutely became a blazing hot piece of metal. So it really just depends on the situation.
Yeah, I mean, I agree. If you don't have a tight fit and you introduce, what is 1,000th of air, 1,000th thickness of air, has the same thermal resistance of an inch of H13 tool steel, right?
Right.
So but you can model that in. Okay, you can you got to have some running fit if you're going to put it in, or you can shrink fit these materials in which case you really drop down the contact resistance between the two. Okay, I'm sorry, I didn't mean to go off base with that, but I hear
no,
that
it's
a
important.
lot, and I'm always.
Go ahead.
I'm sorry, I cut you off. I'm sorry.
I was going to say.
Go ahead.
There are ways to at those interfaces to change the thermal resistance at those interfaces as well within Moldflow. So those are things that you can play around with. So and you can see the change in the heat transfer based on whether you have that 1,000th air gap or a press fit or whatever. There are ways to change that heat transfer coefficient at the interface between inserts and so forth as well.
Okay. All right. Well, thank you, Tim. I appreciate your answers.
You're welcome. Okay, we'll have time for one more question, I think, before we jump off. David, I see your hand raised still. I don't know if that's from the previous question or.
No,
I didn't know if you had a follow-up question there or not.
No, I'm drinking coffee instead of pressing buttons. How's that?
Gotcha. Okay.
Okay.
All right. Well, it doesn't look like we have any other questions, so we'll leave it at that. I appreciate everybody, like I said, joining. Feel free to email me if you have any further questions. Be looking for information on our next webinar. Like I said, it's going to be another Back to Basics, and we'll be talking about warpage analysis at that point. So thanks, everybody, and have a great day.